Hello and welcome to this quick review of bonding types and the resulting structures you get from them. As always, before you start, make sure you've done some independent study and written some notes up on this topic so you have an idea of what's coming up. It would be helpful to have this work in front of you when you're watching the clip, because the clip is designed to support the work that you've already done. So obviously when it comes to bonding, quite a lot of the basic ideas will have been covered by you already at GCSE. So don't expect me to dwell for long on these, out of respect for the fact you'll know something about them already. I'll just use them as a set of context. This is just to let you know that some of the things that I might mention from time to time will be familiar already. So one of the first things we need to do at A level is start to move away from the simplistic notion of sharing an electron pair to describe covalent bonding. There's a little bit more to it than just that, as you'd expect. So the electron pair is actually shared, so the idea learned at GCSE is not wrong, it's just slightly limited in its application. The bond is actually an electrostatic attraction. So as the diagram suggests, a covalent bond is actually the electrostatic attraction between a bonded pair of electrons and the nuclei of the bonded atoms. So obviously this happens because the electrons and the nuclei have opposite charges to each other. And you may also recognise some similarities between the diagram and also the dot-cross diagrams, like the ones you've come across before. And that's because this is what a dot-cross diagram is representing when we're dealing with covalent bonding. So the first thing to do if you're drawing a dot-cross diagram is draw the two shells, the two outer shells of your two atoms, with a substantial overlap. The overlap's important. The reason it's important to overlap the two circles, not just touch them, is because the overlap indicates the actual overlap of the atomic orbitals the electrons are contained in. This is because covalent bonding only occurs if atomic orbitals overlap. So let's assume that for the sake of this clip, this bond is between two chlorine atoms, such as a Cl2 molecule. And as you know already from GCSE, a chlorine atom has 7 electrons in its outer shell and needs 8 to complete its octet. In this case we're dealing with two separate atoms, so one gets crosses for its electrons and the other one dots, even though they're the same element. So you start by creating the covalent bond. The next thing to do is place the electrons in pairs on the shell. If they're not on the shell, you're implying in your answer that they're not contained in an energy level. If they're not paired, you're implying that they're in separate orbitals. The problem with stating these two things is that neither of the statements are true. Accuracy in your dot-cross diagrams is essential. So if you're ever unsure, always refer to the textbook your exam board uses. There's lots of different versions of these types of diagrams online, some of which are much less accurate than others, so be very careful of just going onto the open internet to check. Always go onto your ebook or your textbook in your hand that your exam board or your college is using, because that's the one that your exam will be based on. So let's now use oxygen as an example to deal with double bonds. So each oxygen atom has 6 electrons of its own in its outer shell, so it needs access to a further 2 in order to complete its octet. So in oxygen's case, because one covalent bond, a single covalent bond, only allows an atom to share 1 extra electron, to achieve this in oxygen a double covalent bond is needed. So this time I'm going to draw in the dots and crosses by hand to make sure I'm showing you properly how to do it accurately. So I draw in the double covalent bond first, with dots and crosses alternating. So we do this because an orbital from each oxygen atom has just overlapped. The alternation shows 1 electron from each atom. So with the little grey box I've just highlighted one of these overlaps. So now I've just put in the requisite number of non-bonding electrons on each outer shell. And it won't surprise you to find out that non-bonding electron pairs are called lone pairs and bonded pairs of electrons are called bond pairs. We make use of this idea when we determine the shapes of molecules, which is covered in a separate clip in a separate lesson. Now, a slight variation on the covalent bond is a dative covalent bond. The only difference here is that one of the bonded atoms donates both the shared electrons to the bond. And the example we have here is called the ammonium ion. Now, all these dot-cross diagrams are all well and good because they give us detail about what's going on. But if we're trying to draw out a molecule or a bond quickly, in a way that's convenient to us, it's going to take a lot of time to draw in the electrons. So to speed things up, we usually draw a solid line between the symbols for two atoms to represent a single covalent bond in chemistry. So it's worth reminding you that you only need to draw a dot-cross diagram if you're specifically asked to in a question or task. So these are how the examples we've just looked at might be represented. The arrow points away from the nitrogen to the hydrogen atom in the ammonium ion because it is nitrogen donating the 2 electrons in this case. So the arrow could just as easily point the other way, as fluorine is donating the electron pair in this Bf4- ion below left. So it's also worth pointing out that you can get triple bonds as well. You've probably come across them at GCSE. So if we were to look at nitrogen, for example, why don't you pause the clip and try to draw this one. So first of all, the substantial shell overlap will allow you to draw the 3 dot-cross alternations, like so. So you've got to be careful here. You need to think, how many electrons does each nitrogen atom have in its outer shell to start with? Now, because nitrogen is in group 5, that must mean it's got 5 electrons in its outer shell. Not forgetting that wherever possible, non-bonded electrons need to be paired up. We now have a triple bond which allows each atom to have a complete octet in its outer shell. So this molecule has one dative covalent bond and a triple bond between the carbon and the oxygen. But what if you had to draw this out as a dot-cross diagram? So clearly what we'll need to do is, just like we did for nitrogen, allow a substantial overlap between the shells. Now, applying the same logic as we did before, think about how many electrons each atom has in its outer shell before it undergoes any bonding. So if we bear this in mind while we draw the triple bond. So if we think about it, if there has to be a dative covalent bond somewhere, oxygen has more electrons, so it's more likely to be able to donate 2 electrons to a dative covalent bond. So I've now added the arrow to show the dative covalent bond in my triple bond, and I've also put in the electron pair from oxygen, so crosses are going to be representing the electrons from oxygen. So we've now completed the triple bond, including a dative covalent bond. So we still need to account for the remaining electrons in each atom's outer shell. So by adding an electron pair to each atom's outer shell, we now complete their octet. We've taken account of the number of electrons that each atom had in its outer shell to start with, and our 3 criteria have been met. There's a dative covalent bond, there's a triple bond, and each atom has 8 electrons in its outer shell. So the structure of a substance refers to how the atoms, ions or molecules are arranged on a larger scale. It is not the same as the bonding between individual atoms or ions. So covalent substances tend to form simple molecular structures. So simple molecular structures involve covalent bonds between atoms and molecules with weaker intermolecular forces between them. It's very important to remember that when these substances melt or boil, it is these intermolecular forces which are broken, not the covalent bonds. It's very important not to get confused about this, because this is one of the major mistakes that people make when they're explaining structures. It is not the covalent bonds that are broken in simple molecular structures, it is the intermolecular forces which are broken. The only exception to this would be giant covalent structures such as graphite, diamond or silicon. These have many covalent bonds which need to be broken before melting occurs. So covalent bonds are strong, so they require lots of energy to break. So ionic bonding needs to include the description electrostatic attraction between oppositely charged ions. So as you can see from the picture, the ions alternate in the structure, positive then negative. So when you draw the dot-cross diagram for an ionic compound, we generally draw the positive ion on the left and the negative ion on the right. We also use square brackets, charges outside the square brackets, and only the outer shell in each ion's case. You add the outer shell electrons the negatively charged ion or anion had before it became an ion, so in this case there are 7. You leave the cation's outer shell empty, and finally you add any gained electrons to the anion using a different symbol for the gained electron. So looking at examples with different numbers of each ion type, in other words not in a 1-to-1 ratio. So I'll start off by taking you through sodium oxide, then I'll pause the clip and you need to try strontium chloride. So for reference, I've also put the instructions for doing it on the right hand side in a box. So let's start by drawing up the square brackets for sodium oxide. The oppositely charged ions have to be next to each other. Now remembering that the oxide ion is 2-, that's why I've put that charge in. You can either draw them using this configuration, but because we're a little bit short of room I'm going to do it a slightly different but equally acceptable way. Okay, so you can do it that way as well. The important thing to remember is that the square brackets that butt up next to each other are oppositely charged. So that arrangement might lose marks because you've got 2 positively charged ions apparently attracting to each other. So the highlighted part implies 2 positive ions attracting, which wouldn't happen. So I've drawn up my square brackets with the oppositely charged ions next to each other, and the charges are drawn outside the bracket. The outer shells only are shown, and the cation shells are empty and just drawn as a circle. Now the anion shell contains its own electrons in one symbol and gained electrons in another symbol. But notice how the gained electrons are paired up with one of the original outer electrons from oxygen. The reason for this is when electrons are gained, partially filled orbitals with 1 electron now have 2. So looking into this a little bit deeper, this is the original oxygen atom's electrons, or 1s2, 2s2, 2p4. And I've now highlighted the outer shell electrons. So I'll ask you to focus on those ones there, the 2s2 and the 2p4, in other words, the second outer shell. So 2 electrons are gained. The outer shell has 8 electrons, but to achieve this, incoming electrons had to be paired with existing ones. So now why don't you have a go? Grab a scrap of paper or whiteboard, pause the clip, and do the same for SrCl2, strontium chloride. Use the box with the instructions. I'll keep it up there so you can use that to guide you through the process. So hopefully you got something approaching what we've got here, and it doesn't really matter where you put the incoming electrons in the anion. So now let's quickly deal with the structures that you get and some of the properties with ionic bonding. So the main sort of properties that ionic compounds will exhibit are these. You need to be able to explain these clearly or the reasoning behind them. So the high melting and boiling points are due to many strong electrostatic attractions needing to be overcome, which requires energy. So molten or aqueous states means ions are free to move and carry charge, but in solid form they can't. It's important to remember that the electrons are fixed in ionic substances because they've been gained by the anions. So even in liquid or aqueous form, this is still the case. So the electrons are never the charge carriers. In this case, it's the ions. And finally, on ionic bonding, the name of this type of structure is called giant ionic. It's important to remember this when you're doing longer answer exam questions of the descriptive style. So our final type of bonding is metallic bonding. This is the electrostatic attraction between positive metal ions and a cloud of delocalized electrons. So often you'll be asked to draw this out as a diagram, so it's really important that the positive metal ions and the delocalized electrons are clearly labelled. So it's important, depending on which metal you're actually asked to draw out, to pay attention to the actual charge on the ions. So you make sure that you've labelled them up as 2+ in the case of barium and 3+ in the case of aluminium. So not forgetting our electrons. So you can either label them directly like I've done, or you can use a key like the graphic shows. It doesn't really matter which way around you do it so long as it's clear. So remember, when you do this in an exam or test, or even a homework, provided it's clear and not confusing, the marker or the examiner will award you the marks that are on offer. So if we look at the features of metallic bonding, we've got electrical conductivity, strong, malleable and ductile, and high melting and boiling points for the reasons given on the screen. It all comes down to the attraction, or the electrostatic attraction, between positive metal ions and the cloud of delocalized electrons. But let's look at different metals. If you look at the shading that I've added to the barium and aluminium lattices, or structures, the shading indicates the density of the electron cloud. What I mean by that is that for every barium 2+ ion, there's 2 electrons added to the electron cloud. For every aluminium 3+ ion, there's 3 electrons added to the electron cloud. This means that aluminium will have a greater charge difference between each ion and an electron. The ions are 3+, the electrons are 1-. That's a charge difference of 4. This means that anything that involves overcoming the attraction between the positive metal ions and the cloud of delocalized electrons will be more enhanced in aluminium. So aluminium will be stronger because it will take more force to overcome them, and it will also be higher in melting point and boiling point compared to barium. So if we think about descending a group of metals that is, such as group 1 or group 2, there's obviously more distance between the positive nucleus and the delocalized electrons. This gives you electrostatic attraction being lowered between the ions and the delocalized electron cloud. So metals get weaker, and then the melting point and the boiling point as a result decreases. So that concludes our sort of overview of bonding and the structures that result from it with their features. Thanks for listening, and see you again next time.